Assalamu alaikum warahmatullah. Good afternoon, Doctor. Balaraga Ali Gambo from Group 2 member. Here are some, this is the schematic circuit diagram that I wanted to be or that I want to design. As you can see here, this is my AC voltage source, that is the input voltage. This is my transistors, 4 transistors. This is my flow of current. This is my load resistance, and then this is my output voltage. So in this design, I will only focus, I said, for the design. This is how it's going to be. So at the moment, AC voltage applied, that is 240 and 50 has the frequency. T1 and T2 will conduct, that is during the positive half cycle, while T3 and T4 will be off. So during this time, the current will flow through T1, through the load resistor. It comes to transistor 2, and it goes back to the AC voltage source. However, during the negative half cycle, it's in the opposite direction. It means that T3 and T4 will conduct while T1 and T2 will be off. This is how the current it's going to follow. This one, it follow here, it come back here. So this is some calculations that I made for the B output average, I output average, however, and B B output root mean square. This is some outputs. This is some calculations that I use for this type, and also for the firing angle. I also use some calculation for the gate 1 and the gate 2. This one I will explain more in the Matlab. As you can see here, this is the simulation in the Matlab. This is my AC voltage source. This is my 4 transistors, that is T1, T3, T2, and T4. This is my current measurement, voltage measurement. This is my load resistor. This is my scope in order to see the output waveform. This is my false generator, that is false generator 1, false generator 2. This is my from go to in order to connect the false generator. As I was explained in the previous before, this T1 and T2 will conduct during the positive half cycle, while T3 and T4 will conduct during the negative half cycle. I also use voltage measurement parallel with this AC voltage in order to measure the input voltage. However, I also use current measurement in series with the load resistor in order to measure the output or the output current. I also use voltage measurement in order to connect it in parallel with the load resistor in order to measure the output voltage. This is my scope, for example. If I want to see my output voltage, my wave, this is my input voltage, this is my output voltage, this is my output current. So doctor, here you can see that it's different from this one. Why? Because of the firing angle. This is how it's begin. So for example, as you can see here, I selected my firing angle to be 60 degree. So it's what happened from this is the calculation that I want to explain. This is my amplitude for the gate 1. I selected amplitude 1, period 0.02, that is fault width, that is 5. The phase delay 0.003. However, for the second gate, also like this one, amplitude 1, period 0.02, false, phase delay, this one. So this is this because of the firing angle that I selected it. Also, it will start at 60 degree.
Assalamualaikum. My name is Muhammad Hanif Imam Samsubahi, and in this assignment, I will present about the bridge rectifier with capacitor that as the load. So, bridge rectifier is an electronic circuit that convert an AC to DC voltage. The basic design of a bridge rectifier involves 4 diode. That's here that I use transistor in the Matlab simile arranged in a diamond pattern. And the AC input voltage is applied across the two terminal here of the diamond pattern, while the DC output voltage is taken from the two remaining terminal from here, negative. So the diode in the bridge rectifier allow the current to flow in only one direction during positive half circle of the AC input voltage. Is here at the resistor and resistor 2. The gate 1 and gate 1 here. So during the negative half circle, the opposite diode conduct current that here from here, resistor 3 and resistor 1 here. As you can see, it get to at both of the diode. So the switching of the current direction result in a unidentical current flow, which is the basic principle of the rectification. The design of the bridge rectifier should take into account the voltage and the current rating of the diode used, as well as the load impedance. The diode should be have a sufficiently high voltage rating to withstand the maximum input voltage and the current rating to handle the maximum current flow. So next, I will run the simulation. And in here, the AC voltage the input I use is 120 times with square root 2, and while the frequency is 50 hertz. So next, at gate 1, I use the amplitude is 1, and the period for this measure is 0.02 at 0.02. Yes, the pass wide is 5, and the phase delay is 0.033. For the phase delay, this is the result that I get after I use for the 60 degree here, the calculation here, 60 degree, the ratio 60 degree divide with 360, that I get 0.166, and after that I divide it with the frequency, that is 50 hertz, and lastly I get 0.033 second. So for gate 2 is almost the same, but it a little delay from gate 1, that is gate 2 delay is equal to gate 1 delay plus 1 over frequency times with 1 over 2. So the gate 2 delay is 0.0133 second. So next, I will run the simulation without the capacitor first, and it is ready. Okay, next. Okay, this is the result that I get. The after I run the simulation without the capacitor, this is happen because of the 60 degree phase that I use. That is 0.0033 second. Yeah. So after that, I run the simulation with the capacitor. Okay, wait. Okay. The first value of the capacitor is 1 millihenry and 1 millifarad, and I run it. So and here we can see that the capacitor be used to reduce the voltage ripple and also the current ripple. The ripple voltage is the AC voltage component that remain after the DC voltage have been smoothed out by the capacitor. The increasing of the capacitor will reduce the ripple voltage, result in more stable DC voltage input. Okay, after that, lastly, I will increase the capacitor value about 50 milli. Okay, apply. You run it. Okay. At here, we can see that the voltage have been reduced, the ripple have been reduced, that it almost have no voltage, have no ripple in the output. So that's all for me. Thank you.
Hi, my name is Suresh Ankrajan. My media number is HE220041. So today I will explain about my circuit, where my circuit is an single phase half wave control rectifier, where you can know that a control rectifier is a type of AC to DC converter that provides adjustable DC output voltage from the given AC input supply. For a control rectifier, we will using a thyristor instead of diode. A thyristor is a SCR, a silicon control rectifier. So for my, where you can see here, for my voltage supply, AC voltage supply, my peak voltage is 120 square root of 2. I'm using a frequency of 60 hertz. So from there, my R load is 100 ohm. So from there we can have our alpha, where alpha is equal to cos shift cos times by V naught times by 2 pi over Vm negative minus 1. So our alpha will get 61.2 degree. Meanwhile, for the pulse generator, we need to change the period. The period is equal to 1 over 60, where we will get 0.0166, and the phase delay is uh, equal to phase ratio times by uh, period ratio, where phase ratio is equal to alpha time by alpha ratio is equal to alpha divided by 360, where we will get then where our alpha is 61.2. Then from there we can get phase delay, where our phase delay is 0.0028 second. So where it's all been connected, our stop time we adjusted to 0.06. So we run the simulation. So meanwhile, you can know that since thyristor is a continuous device, since thyristor is control device, to control the pulse of generator, we need to add pulse generator. Series resistor is the load for the circuit. Okay, this is the load for the circuit. So after we run it, we can get our simulation result. So you can see here the simulation result for our single phase half wave control rectifier. Okay, after that we change the load to resistor and inductor load, where the inductor we set to 10 exponent negative 3. So we try to run it. It's done. We double click the scope, so we will get the simulation result, where you can see at the third graph is an V output from the load. So you can see there's a little bit fluctuation on the graph because of the inductor. Okay, so we need to clarify it. We can adjust the inductor value, inductance value. So we can adjust to 50 exponent negative 3. Apply. Then we try to run it. So you can see the fluctuation has been done at the graph because of the inductor. Okay, that's all from me. Thank you.
My name is Aina Debati Zulkifli. My metric number is HE220040. So here I do the single phase half wave uncontrolled rectifier. So here I use AC voltage source, and I have the diode. I have have the current measurement, voltage measurement, and then this one I use the series RLC branch, and this one is my main block, which is a power grid, and this one is scope. And then so here I use the RLC branch. Why I use the RLC branch? Because it have two, which is RLC load and RLC branch. So this both for single phase. So RLC load is basically based on the power rating of the device. So let's see. There is difference between load and branch. So if we see here, RLC branch, we need to select R value, L value, and C value. Whereas if you see the RLC load, what is power rating, reactive power, and what is the voltage of VRMS of the load and inductive, and then the reactive power of the capacitor and inductor. On that reactive current need to select either no value of R, L, and C, or no power rating according to that. So I can define our system like our rectifier or inverter. So in this I require RLC branch, so that I can define my R, L, and C. Okay, so here I have my RLC branch, which is load. I need first of all one R load. Want to see how R load is working. Okay, so here is the R load. So this voltmeter here, I connect positive side to the positive terminal, negative side to the negative terminal. So this is voltage of output voltage. Same here, at AC source, the positive side connect to the positive terminal and the negative side connect to the negative terminal. So I connect the input voltage to the first port of the scope, and second one is the output, and the third one is the current. So now I will do is my AC source. What is my AC source? If we talk about real actual source, which is present at our homes, there is our 230 volt, but 230 volt is our RMS voltage, but not the peak amplitude. So basically, if I want to pick RMS is watt maximum by root 2, the maximum value I want, that is R minus into root 2. So 230 in root 2 is, so it's around 1.414, and for frequency is 50. So okay, and R I will keep this as 10. Okay, fine, let's run. So we can see the waveform, this is not coming pure sine. So what I will do is click the model settings. In this we have to change our configuration parameter. Let's see the solver. So I will select this discrete and okay, and in power GUI also we need to change discrete. So okay, so let's run it again. So yeah, as you can see now, it's come a pure sine. Now I change value R to RL. Okay, so let's imagine when R load is there, it is conducting 0.8 like that, it is getting turned off. But when L is also connected, what will happen? So let's run. So as you can see now, it is conducting very small at here, very small, and it is getting negative waveform. So we have to see more clearly. I will just increase the value of inductor. So here I will put, so we put 10. Okay, and then let's run it again. So here we can see it clearly, it is operating at negative region also. Now I connect to R, L, and E. That is our DC motor also we call. So I take the DC voltage source and I keep this here, and also I keep the value as 100 only. So now what will happen? So let's imagine it is 100 volts. So what will happen? So let's imagine it up to 100, my current should be 0, and after 100 it should start conducting. That is my diode. Okay, let's see whether it is following that or not. Okay, yes, as it is following. See, it is started from 100 and it is operating, and it is going from negative also. So that is the RL and E for single phase uncontrolled rectifier. Thank you.
Assalamualaikum and hello to everyone. My name is Nuraumi binti Adam and my matrix number is GE220028. So today I would like to present my part, which is my part is about the center tap full wave rectifier. As we know, center tap full wave rectifier is a type of rectifier which use a center tap transformers and two diodes to convert the complete AC signal into DC signal. And the center tap full wave rectifier is made up of an AC source, a center tap transformer, two diodes, and a load resistor. So next, I will tell more about how the center tap full rectifier works. So at first, the center tap full wave rectifier use a center tap transformer to convert the input AC voltage into the output DC voltage. And then when input AC voltage is applied, the secondary winding of the center tap transformer divides this input AC voltage into two positive and negative. During the positive half cycle of the input AC signal, terminal A become positive, terminal B become negative, and center tap is grounded 0 volt, as we can see at here. So this one is terminal A at diode 1, and this one is terminal B. So next is the positive terminal A is connected to the P side of the diode D1, and the negative terminal B is connected to the N side of the diode D1. So the diode D1 is forward biased during the positive half cycle and allows electric current through it. So this I will add Matlab. At here, we put the forward voltage as 0.8. Meanwhile, for the AC voltage, we put as 60 frequency, 60 Hz, and the peak amplitude we put as 120. So we run it. So after we run it, we could get the waveform like this. So this is AC signal waveform. Meanwhile, at here is signal of output. So if a small voltage is wasted at the diode D1 and diode D2 to make them conduct, however, this voltage is very small as compared to the voltage appear at the output. So this voltage is neglected. The diodes D1 and D2 are commonly connected to the load RL. So the load current is the sum of individual diode currents. We know that a diode allows electric current in only one direction. From the above, we can see that both the diode D1 and D2 are allowing current in the same direction. Also, we know that a current that flows in only single direction is called a direct current. So the resultant current at the output load is a direct current. However, the direct current appeared at the output is not a pure direct current, but a pulsating direct current. The value of the pulsating direct current changes with respect to time. This is due to the ripples in the output signal. This ripple can be reduced by using filters such as capacitor and inductor. The average output DC voltage across the load resistor is double that of the single half-wave rectifier circuit. That's how the output waveform of full wave rectifier. So that's all from me. Thank you.